Hello, my name is Tobias Ried. I'm a group leader in Felix Otto's group, and in this talk I want to present to you a variational approach towards the regularity theory of the Monge-Ampère equation, or rather optimal transportation, with interesting applications to the matching problem. Here you can see all the people involved in this project, current and former members of the group, as well as our external collaborator Martin Huisman in Münster. Optimal transport is and has been quite an active area of research, quite a popular subject in mathematics, both in theory and applications, and it has driven numerous important developments in partial differential equations. In this short presentation, I want to show you how it connects to highly active and current research projects in both in theory and applications, in particular how it connects to the matching problem, to the regularity theory of partial differential equations, and to the calculus of variations through the Giorgi's approach to the regularity of minimal surfaces. So let me start by briefly describing the optimal transport problem. Given two measures, mu and lambda on Rd of equal mass, the goal is to transport all the mass, which you may think of as being made out of small particles, from one pile to the other, and to do that in such a way that it is optimal with respect to a given cost function c, which tells you how expensive it is to move a particle from position x to y. Optimal transport then means minimizing the total transport cost among all couplings between the initial measure mu and the target measure lambda. Existence of such an optimal coupling follows by rather soft methods using the convexity of the problem, using that the problem is completely convex. Then for the quadratic cost function, so the Euclidean cost function where the cost is given by the Euclidean distance squared, the optimal transport actually induces a rather natural distance between, or squared distance between probability measures, the so-called Wasserstein distance, which also connects to applications in statistics and probability, because it gives you a way of coupling two random variables in such a way that the covariance is maximized. In the following, I want to focus on this quadratic case only, and let me specify and simplify even further by assuming that the target measure lambda is given by Lebesgue measure. Now, what is the connection to the Monge-Ampère equation? Roughly speaking, the Monge-Ampère equation is the Euler-Lagrange equation of the variational problem, that is the optimal transport problem. More precisely, it follows from convex duality that the support of the optimal coupling P is contained in the graph of the subdifferential of a convex function, the so-called Kantorovich potential psi, and then spelling out the transport condition, namely that the gradient of psi pushes forward the initial measure mu to the target measure lambda. What this means, then by a change of coordinates, this formally leads to the following PDE, namely that the determinant of the Hessian of psi is equal to mu. This is an instance of the Monge-Ampère equation, a fully nonlinear elliptic equation that has received quite some attention in PDEs, and whose regularity theory is rather delicate because its ellipticity is degenerate due to invariance under affine transformations. In a series of beautiful papers, Caffarelli actually was able to achieve a breakthrough in the regularity theory of this equation, building upon comparison principles. So this somehow shows you that the Monge-Ampère equation is quite an important and interesting equation, and it is at the crossroads of two important types of nonlinear PDEs, namely fully nonlinear on the one hand and variational on the other hand. Singularities in optimal transport are quite generic, and in this sense the Monge-Ampère equation is an interesting nonlinear equation because it shares the feature that interesting nonlinear equations typically have, namely that smooth data do not lead to smooth solutions. And there's actually quite an easy and intuitive example due to Caffarelli, and let me guide you through this a little bit. So Caffarelli starts with an initial measure that is given by the characteristic function of a ball, And then it's not too hard to see that if the target is highly non-convex as depicted here, so for instance such a dumbbell type shape, then the transport map has to be discontinuous. In a more subtle example, Grégoire Löper was able to extend this to a Riemannian setting where the cost function is given by the Riemannian distance squared on a manifold, and he was able to show how curvature also enters and can produce singularities. And this all shows that what is called epsilon regularity is of interest because in general, given even smooth data, you cannot expect the solution to be regular. Now, epsilon regularity is quite an important notion in regularity theory, and it is typically the first step in a more detailed analysis of singularities. Epsilon regularity roughly means that if a suitable quantity is small enough, then you're in the smooth regime in the sense that smooth data lead to smooth solutions. In the optimal transport problem, it means that given that the transport energy locally falls below a certain threshold, then can you show that you have epsilon regularity in the sense that if the measures mu and lambda are locally smooth, then the Kantorowicz potential is locally smooth. And this has indeed been shown to be true by Figali and Kim, and later in a work by De Philippis Figali, and both these works build upon Caffarelli's theory. In our variational approach, epsilon regularity relies on completely different methods. Namely, it exclusively makes use of calculus of variations tools, in particular a harmonic approximation result, which can be stated as follows, namely that if the same type of smallness condition holds, that the local transport cost falls below a universal threshold epsilon, and assuming that the measures mu and lambda are locally close to the uniform density, then the displacement y minus x, which describes you how particles are moved from position x to y, can be approximated locally by a harmonic gradient field. And this is in spirit quite similar to the Giorgi's approach to the regularity theory of minimal surfaces, where the minimal surface M at a given scale is locally approximated by the graph of a harmonic function. Now let me tell you next how to construct this harmonic gradient field, or at least give you the ideas how one can how one can get this harmonic gradient field. And to this, it's quite good and it's quite helpful to change perspective on optimal transport on the, a bit. In particular, I want to show you a beautiful result by Jean-David Benamou and Yann Brenier, namely that there is a more fluid or Eulerian point of view to the optimal transport problem. More precisely, so far I've introduced what one might call the Lagrangian side of optimal transportation, in the sense that the transport plan induces trajectories along which the mass, and again think of mass as being made out of small particles, so it describes how the mass moves along trajectories from the initial density to the final measure, and thereby connects the mass at time 0 to the measure at time 1, and also induces a natural notion of interpolation rho of t between the densities. These trajectories now can be thought of being derived from a flux J, which together with the density rho satisfies the continuity equation dt rho plus divergence of J is equal to 0, with boundary conditions that rho at time 0 is given by the initial measure mu and rho at time 1 is equal to lambda. Then the optimal transport problem for quadratic costs, so the Wasserstein distance, square Wasserstein distance, can completely equivalently be described by the following dynamical version of the optimal transport problem, namely minimizing the kinetic energy among all density flux pairs rho j that satisfy the continuity equation and connect the initial measure mu to lambda. So what is the advantage of this formulation? First of all, it reveals a strict convexity of the problem that is not easy to see in the original formulation, but here it's completely obvious because the kinetic energy density is a jointly strictly convex function both in rho and j. On the level of the harmonic approximation, it means that on the level of this Eulerian picture, a harmonic approximation means approximating the Eulerian velocity field j over rho by a harmonic gradient field. And on the next slide, I will show you how using this Eulerian reformulation, one can actually quite easily get to such a gradient field. Namely, the harmonic gradient field grad phi is constructed by the solution of a Neumann or flux boundary value problem, where the boundary values on a given ball of radius r the flux boundary values are induced by the time average of the Eulerian velocity field j corresponding to our optimal transport between mu and lambda. And then of course we make an error because we're looking at the time averaged flux here, but it turns out that we can control the error between the time resolved flux boundary flux j dot nu and its time averaged version by a boundary layer construction, and to show that the error we make there is actually small, non-linearly small, and therefore doesn't play a role in the estimates. And incidentally, this boundary layer construction is based on isoperimetric principles of higher codimension, and thereby also connects to earlier works on pattern formation and branched optimal transportation in superconductors, and again makes this point that guided by applications which give us somehow a good intuition for the problem, we can get a good viewpoint on the theory and make some progress there. Then in a final step, we can use strict convexity, which is apparent in the Eulerian formulation, to convert the energy gap between the energy of the optimal rho j and the energy of this approximation by a harmonic gradient field to convert this into a distance between rho j and the harmonic approximation in the Ried topology. Now, of course, this was just a very rough sketch of how we get this harmonic gradient field, but I hope it shows you what the ideas are that lead to our result. On the next few slides, I want to focus now on applications, and let me start by actually a new application, which is to the matching problem between Poisson and Lebesgue. In the language of optimal transportation, this can be expressed as wanting to find the optimal transport between a random measure that is actually a measure that consists of random Dirac points, random points sitting at the points of a Poisson point process downstairs, to Lebesgue measure, to unit mass Lebesgue measure upstairs. And what's going on can be roughly seen here in the picture. And let me actually assume that for simplicity, everything takes place on a finite torus of side length L, and that the Poisson point process is approximated by throwing in L to the D, which corresponds to the volume of the torus, L to the D points uniformly at random independently into the torus. And then through the optimal transport map, these points are mapped to convex cells upstairs, which then also give rise to a random partition of the torus upstairs. This matching problem is a problem with many facets. It somehow all started out in the computer science community, where the question was more about matching one version of a Poisson point process to another realization of the Poisson point process upstairs, but then later also was taken up by probabilists like Talleyrand and Ledoux. Also, physicists have been interested in the problem, especially the group around Giorgio Parisi, and they actually were able to give some some intuitive heuristics of how one can understand this problem. And this is something that I also want to explain on the next slide. And then quite recently, it was also taken up by the analysis group in Pisa around Luigi Ambrosio. So let me show you a bit the physicist's heuristics. Again, let me remind you that if we look at the Kantorovich potential psi, then this formulae satisfies the Euler-Lagrange equation, namely the Monge-Ampère equation, determinant of the Hessian of psi is equal to mu, where mu now is this measure that sits at random Dirac points. Now, on large scales, this measure mu actually behaves like white noise, or rather white noise shifted by 1, which is the average of these Dirac points, on scales much larger than 1, where much larger than 1 here means really much larger than the intrinsic distance, or the intrinsic scale of the problem, that is the distance, the average distance between the Poisson points. Now, even though white noise is rather rough on small scales, on large scales, it can actually be seen due to cancellations as a small perturbation of the identity. And therefore, it makes sense to write the Kantorovich potential of the optimizer as 1/2 x squared plus a small perturbation v, which then solves the following equation, namely that Laplace v is equal to white noise xi, and that easily follows by linearizing the trace, the determinant around the identity, which gives the trace, and using that the trace of the Hessian is equal to Laplace. Hence, on large scales, we would expect that the displacement can be approximated by the gradient of v, which, as the solution of this linear stochastic partial differential equation, should behave like the Gaussian free field. And this large-scale linearization is actually analogous to a large-scale regularity theory in stochastic homogenization pioneered by Avellaneda and Lin in the 80s, and then with important contributions by Armstrong and Smart. And in this way, it also connects to another active research area in our group. More precisely, the result reads as follows, namely that with overwhelming probability, in the sense that we can control arbitrarily high stochastic moments on all mesoscopic scales R, which are much larger than the intrinsic scale 1, the distance between Poisson points, but much smaller than the size of the torus, which you should think of the macroscopic scale. So on such mesoscopic scale with overwhelming probability, the distance between, the displacement can be approximated by gradient V, this field that behaves like the Gaussian free field, which, and this distance in dimensions less than 4 is actually much smaller than the variance of the object that you're assimilating to. Now, this result also shows a fundamental difference between dimensions d bigger than 2 and dimension d equal to 2. And in this sense, d equals to 2 is actually the most interesting dimension, because the object you're assimilating to actually diverges as the size of the torus L goes to infinity, whereas in dimensions higher than 2, it stays bounded. And this feature is similar to the corrector in stochastic homogenization. Now, before finishing my talk, let me mention another quite interesting application, namely to partial regularity of optimal transport maps. So partial regularity essentially follows from epsilon regularity plus an important result from measure theory, namely Alexandrov's theorem about the almost everywhere twice differentiability of convex functions. And in a series of works, Goldman and Otto and Goldman were able to somehow give the variational counterpart of Figali-Kim and De Filippis Figali for the Euclidean cost functions, which Felix Otto, our PhD student Maxime Prudhomme, and I were quite recently able to extend to general cost functions. And a key concept in this generalization to more general cost functions is actually that minimizers with respect to a cost function that is quantitatively close to the Euclidean cost function are almost minimizing for the quadratic cost function. There's also some interesting application to the boundary epsilon regularity. So we can also get, with this variational method, a counterpart to Jen Figali's results about boundary epsilon regularity, which has been worked out by Miura and Otto. But let me mention at this point that the partial regularity at the boundary is still a major open problem in the field. So let me conclude my talk. I hope I was able to convince you that the variational approach is quite versatile and it gives you a more robust path towards the regularity theory for optimal transportation, which is well adapted to rough data and therefore also works in situations where Caffarelli's theory is not expected to work. In the future, we hope that the tools we developed can also be applied to the regularity theory of multi-marginal optimal transport, which is essentially open and also has connections to the regularity of Wasserstein barycenters. We also want to look at the aforementioned partial boundary regularity of optimal transport maps, which is a quite challenging problem indeed. And we also want to study the matching problem, especially in d equals 2 dimensions, and construct an optimal coupling which has the property that it has stationary increments, much like the construction of the corrector in stochastic homogenization. And this last project is actually related to activities within the DFG network random geometric systems with Martin Huisman and our PhD student, our new PhD student, Francesco Martesini. With this, I want to end my presentation. I thank you very much for the attention and I'm looking forward to your questions.